Now we talk about uninformed search algorithms on 4 interesting problems. The first one is the vacuum world problem, which you have already seen in the book. There are 2 dirty square blocks, and we need to clean these dirty square blocks by using vacuum cleaner. The state space is shown in the picture below, and there are 8 world states. So this is more like a tree or a graph, you can say. The vacuum cleaner is in this first square, and both are dirty, and then it can take the actions like move right or left, or stay in the same place, do sucking, and then if they suck, then this becomes clean. And this way there are total 8 different states which are possible for this problem. Now let's see what are the percepts and the different other aspects of the problem. So there are 2 dirty square blocks, and we need to clean these dirty square blocks by using vacuum cleaner, as we have already said. And the percepts in this case are the location and content, that means dirty or not. Possible actions for the vacuum cleaner are move left or L, move right R, suck S, and no operation no op. So the initial state is when vacuum agent can be in any state, okay, left or right, as shown in the picture. So the successor function generates legal states resulting from applying the 3 actions, okay, left, right, and suck. So successor function actually applies the action and generates a new state from one state. Goal test checks whether all squares are clean. That's the goal test will check all squares are clean or not. The path cost will be measured by each step costing 1. So the path cost is basically the sum of steps in the path from initial state to the goal state. Now let's see another problem, which is called an 8 puzzle problem, which is nothing but a particular problem in a group called sliding block puzzles group. And this particular puzzles group is a NP complete problem. So it's a hard problem to solve. But for smaller instances, it is possible to solve by trial and error. And it's not that expensive as well. So the 8 puzzle problem consists of 3x3 board with 8 numbered tiles and a blank space. A tile adjacent to the blank space can slide into the blank space. So we kind of say that, okay, we are swapping the tile with the blank space. Like the blank space is also considered as a tile, and we are swapping a number with the blank space. The objective is to reach the specified goal state. That I'll tell you, okay, this is the goal state and this is the start state. So you have to slide the tiles in such a way that you can reach this goal state. Now, what are the states here? States are the integer location of each tile. Location, please understand. Like for here, 7's location is 1, something like that. 2's location is 2. 4's location is 3. 5's location is 4. Blank's location is 5, in that way. So the successor function, so the initial state can be any state. No fixed state for initial state. Okay, normally we jumble up the tiles and then ask people to reach to the ordered state. So the successor function generates legal state that result from trying the 4 actions to move the blank. Okay, left, right, top, and bottom. So you can move the blank to the left, then 5 will come here. Move the blank to the right, then 6 will come here. Move the blank to the top, 2 will come down, and move the blank to the bottom, then 3 will come up. Something like that. So the goal test checks whether the state matches the goal configuration. And the path cost, each step costs 1. So the path cost is the number of steps in the path to reach from the initial state to the goal state. So you can also have a tree or a graph for this problem solving. And then you can run any uninformed search algorithm to see which path is the best path. Now let's see some more details about the 8 puzzle problem. The 8 puzzle has total 9 positions, okay, 8 number tiles and 1 blank. So any arrangement of this, all these tiles, 9 different position gives you 9 factorial, like 362,880 possible states. Okay, so which is I mean, here all states are not reachable. Okay, you cannot reach all the states because of something which is called parity. So we are not discussing about parity here, but you can understand only half of those states are reachable from any starting state. So 9 factorial divided by 2, 181,440 possible states from any valid starting state. So which is searchable using modern computers. The 15 puzzle problem has 1.3 trillion states. Okay, so and random instances can be solved optimally in a few milliseconds by the best search algorithms. But the 24 puzzle on a 5 by 5 board has around 10 to the power 25 states, and random instances are still difficult to solve optimally with current machines and algorithms. All state space search problems require to find minimum cost path between start state to the goal state. Next, we will discuss the 8 queens problem. In chess, a queen can move as far as she pleases, horizontally, vertically, or diagonally. See here in the adjacent board, like this is a queen, it can go horizontally, vertically, and diagonally. Okay, so you can see that a chessboard has 8 rows and 8 columns. Okay, the standard 8 by 8 queens problem asks how to place 8 queens on an ordinary chessboard so that none of them can hit or attack any other in one move. Like example, see this queen is on the white square and diagonally it can attack this queen. So this is not a correct solution of an 8 queens problem. Anyway, this is not 8 queen. These are 7 queens. So a chessboard has 8 rows and 8 columns. Okay, so where to put the 8th queen? If you ask that question, so you need to first solve that where this one goes. I would think about the 7th queen to put in a place where it will not be attacked by others. Let's say, what if we put it here? One queen goes here. So that might be a place where it might not be attacked. But this queen is on the diagonal path with this queen. Okay? So this is not a correct solution when putting 7 queens. So you need to think about this problem. Now there is analysis of the problem. What are the states? Any arrangement of 0 to 8 queens on the board. Okay, where whatever be the position of it, the arrangements are states. The initial state is of course an empty board. You can keep adding them one by one. The successor function adds a queen to an empty space, okay, by the legal move. So you have to know what are the legal actions, and then the successor function will execute a legal action and then add a queen and make sure, because it's a legal action, that none of them attack each other. The goal test is 8 queens are on the board, but none of them should attack each other. The path cost for each action cost will be 1. So default is 8 because you're adding 8 queens, but the cost will be varied based on number of iterations to take to complete the problem. Okay.